Good morning. This is Albert de Crij speaking from the office of HADEC in Rotterdam, and I would like to welcome all to our webinar series concerning the new chimney design. If I could please ask the attendees to mute their microphones so we have minimum interference of noise on the line, and then we will soon start. Just as a small introduction, this will be about the new chimney design, and the new chimney design is a game-changing improvement for the building of industrial and power plant chimneys. These chimneys will be much more economical to build, and they'll also be much faster to construct, while also being quite reliable and durable as well, as has been proven in practical applications. The big question for our customers is how to properly design and engineer these types of chimneys in such a way that they really fulfill their potential. And that is the prime objective of our series of webinars. It's technical in nature. The first presentation, the first webinar this week will be done by Dr. Philip Gleich of Constructure. It's entitled Design Principles and Key Performance Criteria for the New Chimney Design. And I would like Philip to start this presentation, to take over the screen and to get going with that without any further delay. Thank you very much.
Okay, thank you, Albert, for your introduction. Thank you all for joining us today. It's my pleasure to be here and to present the new chimney design to you. So today I will just present the idea of the concrete structural design and key performance criteria to you. And of course, due to the limited time, I cannot go so much into detail, but please let me know if you have any questions later. You can ask those questions, or if you want, so you can also text me an email, so that's not going to be a problem for me. So just a brief overview for those of you who are not very familiar with that very design type. New chimney design means we do not use any internal flue. So the lining we have, we just glue it directly onto the internal windshield surface. And as a result, you don't need any internal components such as corbels, platforms, compensators, or such. And this is proven to be a very compatible chimney type. It is working in wet stack operation. And due to the very simplified, or rather minimalistic design, you are reducing costs for material and labor, and you also get a very high chimney performance. I want to present some studies we have been undertaking at Constructure, which was formerly entitled Exponent. So those studies are helpful to understand the benefits of NCD better, I hope. And you can also receive those studies, which I will be presenting later, from HADEC or from Constructure on request if you want so. As part of one study, we compared several concrete chimney designs, such as the classical brick flue, which is a little bit outdated because it's not wet stack compatible, and like type 2, the steel, the FRP flue, and the new chimney design. And due to the limited time, I will just be talking about steel FRP flues here compared to the new chimney design. We applied the following specification for designing the chimneys. So we said, like, we want to build a 200-meter high chimney, which is quite a lot. Most of the chimneys right now are, let's say, around 150 meters. It's like openings at 20 meters, the flue during the bypass operation. And we limited the strains to 5 per mil regarding steel and 2 per mil regarding concrete. We of course limited the crack dimensions in the downwash area to around 0.2 millimeters, and in the regular chimney areas to 0.3 millimeters. And here on this sheet, you just see some important construction details of the chimney type 2, the steel FRP flue. So you have all those internal components, such as the lining support, the lining, which is like glued or whatever to the flue itself. You have the compensators, and all those internal parts, of course, are quite costly to install, and you need quite a big effort to bring in the flues into the chimney. And you can arrange that only by that very large access opening at the very bottom of the chimney. So you need a very large access opening, therefore you have a very large chimney, a wide chimney at the bottom. So on this sheet you see the main construction details of an NCD chimney. And I think everybody sees like how simple the structure is. You have a very, as you're just gluing the handguard lining directly to the internal surface of the windshield, you getting a very clean, a very minimalistic design. You don't have any corbels, you don't have platforms we used to have regarding like the brick lining, no compensators whatsoever. So it's a very, very effective construction. But the problem is that you get the temperature much closer to the windshield, and therefore you need to be very careful when it comes to a proper design. So I don't want to bother you too long with any theoretical stuff, but 2 or 3 sheets regarding the way we are working. Considering the nonlinear behavior of concrete, so we are considering the cracking and the material properties, and we are also considering the deformations when it comes to the vertical load-bearing behavior. So on the left, you see like the computation system, and we are dividing such a chimney in many small parts. And in every part, at every point, I can say you need to find your equilibrium between the internal resistance and the external forces. And to achieve that, this is the way we do it. We have our own system and programs we produce. So we are comparing the actions to the reactions in an iterative process, which is very handy to understand. And as a result, you get the strains in the steel and the strains in the concrete, and you can compare these strains to the limit strains you applied, like let's say 2 per mil for the concrete, 5 per mil for the reinforcement. And if there are too high strains, then you need to start your process again, make the diameter a little bit bigger, add some reinforcement whatsoever. And from the strains you can obtain, you get the curvature, you get the rotation, you get the deflection, and last but not least, you get your second order moment, which you will apply again to the moment, and then you start all over again. So this is the way we are designing the chimneys. And just to present you some results of the steel FRP flue, and next sheet would be the regular like pen guard lining chimney. So you see in this case, you have a quite big chimney. You need a large chimney because we said like we have a flue of 8 meters. So we have the mid space that needs a lot of space for the chimney itself. So therefore you have quite wide construction, which is only partly used in the utilization is quite high. From the middle of the chimney, it's rising, but the very top half of the chimney is more or less very, very unused, I would say, when it comes to the strains of the material. And due to the large opening, we need to enter the flue parts. We get a very high reinforcement concentration in this area. So you need to design this area very carefully, and nevertheless, it's a very, very low utilization of the material. And so comparing this type 2 chimney to the type 3 chimney, the NCD chimney, you see you get a much more slender structure, you get a smaller diameter, you get a wind shell which will increase a little bit in certain areas, and we are adding some reinforcement where we need it, and then we get a system which is quite well utilized. So we have a more economic structure, you can say. Also, in the bottom area, you need to do a proper design. You have lots of reinforcements in that area. You have additional reinforcement next to the opening. So this area needs to be designed very carefully. And now you see like the comparison of both structures. The NCD is obviously proven to need less concrete. So if you consider we need, let's say, 1,900 cubic meters of concrete for the type 3, you would need approximately 20% more for the type 2 chimney. So the chimney with an additional steel or FRP flue. And of course, from that, we get a quite lightweight structure, which might be very helpful when it comes to earthquake design, but it might be a little bit problematic when it comes to the design of the foundation, because you need to prevent the chimney from falling over. And when it comes to the deflection, because you have a more slender structure. But it's not only the vertical reinforcement, which is very important for the design process, but it's also the horizontal reinforcement. So I would say that false crack calculations is definitely the major problem of all concrete structures here in Germany. And I think it's maybe the biggest problem of all concrete structures in the world. So you need to do a realistic estimation of the loadings in order to get a realistic estimation of your crack width. And if you're not able to estimate your loadings correctly, you might not only get strong durability problem, but you might also get some serious safety problems regarding the structural integrity of the chimney. So how are we designing the horizontal reinforcement? Again, we are considering the nonlinear behavior of concrete. So the cracking is taken into account close to reality. And from that, we achieve quite economical results. If you're just doing like a linear calculation, it will lead to either too much or not too much reinforcement, which might or will lead to durability problems or safety problems again. And regarding the new chimney design, of course, the most interesting aspect is to estimate the temperature in the concrete close to reality, because this is your main action. So in the following two sheets, I'm just presenting you some design results regarding the horizontal design. So you see again the structure to the left, the wall thickness, and then you see the reinforcement ratio, the steel stresses, and the crack width. And we have limited the crack width in the top area due to the downwash effect. We don't want any large cracks in that area, but we allowed a little larger cracks up to 0.3 millimeters going down from the downwash area. And you can see it's easily possible to find a proper design if you do use the proper design approaches. So in general, when you are comparing the NCD to the like, let's say the flue chimneys, the steel flue chimneys, you get more horizontal reinforcement, of course, because you have the high impact of the temperature. And this is a very complex impact. You need to take that into consideration close to reality. As you can see here, when you see the steel strains, you need to consider that the temperature would be your main impact. And if you're not taking into account the full nonlinear behavior of concrete, you will get false constructions and design results. So as I said before, the NCD is quite a lightweight structure. So as a result, we need a heavy foundation to keep it from falling over, basically. And of course, it's not needed at the type 2 steel FRP flues. We have a very, very large chimney at the very bottom, which is due to the necessity of a large opening for those flue parts. But those foundations of the NCD design in general are a little smaller than compared to the steel FRP flues, which is very helpful if you have only a limited space. So where a steel FRP chimney might not fit in, you might have a chance to NCD chimney. So apart from these, like, let's say, structural design aspects, I want to show you some more studies we had been undertaking. So I will just leave those two chimney comparisons behind, and we will talk a little bit more about the draft performance of chimneys. So we were asked once to compare two chimney types, like type A, I would say it is a NCD chimney, 110 meters high, reasonable diameter of 7.7 meter. And at the bottom, we have a thickness of 45 centimeter, and at the top of, let's say, 30 centimeters. And we needed to compare this type A to another type B. It was a little higher, 120 meters, 8 meter diameter at the top, and at the bottom, as it is a conical design, we get diameter of 14 meters. And we were analyzing the flue gas pressure and flue gas velocity. By the way, it was not me. I'm rather a concrete guy, but colleagues of mine are very familiar with flue gas estimations and calculations. So we estimated the flue gas pressure, and what was interesting to see that, like, the type B chimney has a very, very huge overpressure almost at every elevation in hot summer and spring time. And it was basically the same in winter times compared to the NCD chimney, which those lines you see here, red and the pink line, you get in almost every elevation a significant underpressure. So the conical design has a very poor performance compared to the cylindrical windshield design in this case. And it was not only the performance, of course, which was poor. If you have such a poor performance, you always need more electricity for an extra booster fan. We had in the type A chimney a much lower concrete consumption. We have a much easier consistent reinforcement arrangement. We have a very simple windshield construction considering type A. It is much easier to erect like a cylindrical windshield like type A compared to type B. And you in general get a very good concrete surface quality building a chimney type A. Of course, type A needs high reinforcement ratios at the bottom, but nevertheless, the gains from type A compared to type B always are always dominating. And we always try to build a cylindrical windshield, at least in the area where the flues are. So you see here to the left picture, it is a chimney 95 meters high, 5 and a little bit more meters in diameter. And actually this chimney had been built in Chile, and you will get more information about this chimney in 2 weeks, I guess. And you see it is a very slender design. It is has a wall thickness of 22.5 centimeters at the top, rising a little bit up to 35 at the bottom, but it's a cylindrical, simple design. And you can also arrange cylindrical design, let's say up to 120, 140 meters without any problems. And if you are exceeding maybe 140, 150 meter high of the chimney, you will start to build a rather conical chimney. But we try to build the conical part only below the duct entrance. So in that case, we don't have a pressure loss in the pressure loss of the flue gases, since we having a cylindrical design from the duct opening upwards. So this is very important from my point of view, to keep a very straight and cylindrical design from the point of entry of the duct. Me and my colleagues, we did studies regarding an additional diffuser to the which might be applied to an NCD chimney. You know, like a diffuser, it is very common on steel chimneys, you see it, but it's not common on concrete chimneys. And the idea was to cut like operation costs, to increase the performance, to avoid overpressure, especially in ambient conditions with high temperatures. Yeah, it will increase the overall performance of an NCD chimney. And therefore we did some analysis. We were like analyzing the effect of the windshield diameter, the diffuser angle and diffuser length to the gain you can obtain from the diffuser. And those results are very promising. you can see that if you have, let's say, two chimneys, one without a diffuser, one with a diffuser, you get a strong gain from the diffuser, of course, always depending from its very shape. But this study proved that adding a diffuser to the top of a chimney might be a very, very interesting, good measure to increase the performance of the chimney. And if you increase the performance of the chimney, you will, of course, save electricity for your booster fans. And we analyzed that the production cost of a regular chimney would be approximately around like 6 million US for a chimney 100 meter high with a diameter of 8 meters. So calculating like the extra effort to build a diffuser on the very top, it is like, let's say, between 5 and 10% compared to the overall cost of the chimney. And those savings you get from the booster fan costs, which you don't have because you're saving money due to the better performance of the chimney, those savings will cover the production costs approximately within, let's say, 5 years. It is always quite tricky to design NCD chimneys. If you are considering regular steel FRP flue, you have your requirements from the windshield design, such as you are considering the load-bearing behavior and ultimate limit state, serviceability limit state. You have general construction rules whatsoever. And then, of course, you have the requirements from national standards, especially loadings. But you can calculate the windshield itself rather separately from the requirements regarding the flue design. And this is different when you come to the NCD, because you do first the, let's say, the flue design, you consider your gas volume, flue gas velocity, and so on, in order to determine the chimney cross-section which you really need for the chimney. And then you have to find a way to combine that cross-section with your load-bearing behavior or with your design of the chimney. And that makes it a lot more difficult. And which actually is another challenge is sometimes, especially, sometimes chimney rules and regulations are based for classical chimney types, such as FRP flue chimneys or brick flue chimneys. So the NCD chimney has not yet arrived in all those rules and codes, and therefore we are hopefully trying to develop a technical specification for such NCDs soon. And of course, I was just talking about the design demand, and what is equally important to me is the high quality of the execution and the high quality of the site supervision. I'm sure everybody has hundreds of pictures of chimney construction floors, and we all know what's happening on those sites. And this quality does not, such a poor quality would not fit to a very elevated, high quality design of an NCD chimney. So you have to be very careful when it comes to the execution and site supervision again. So last but not least, some pros and cons regarding the steel flue and the new chimney design. So windshield design, we have a very demanding windshield design when it comes to NCD. You have a very slender construction. You have a cylindrical windshield, which leads to high reinforcement ratios at the very bottom of the chimney. You have high temperatures, and this is very demanding regarding the chimneys. Regarding the general arrangement, it's quite a simple construction. No flues, no internal components. You have a very limited, slender windshield, and therefore you get a low ground space demand. It has proven to be excellent regarding the earthquake resistance, as it's a lightweight construction. It can be built quite quickly. It has low construction costs due to the reduced demand for material and labor, and it is very low in maintenance, and the durability has been proven to be high, which is the topic of the next presentation next week.